Hello students, today we are going to discuss about the energy rich molecules. So the first question that comes to mind is that what are energy rich molecules? Now in the biological systems, there are certain molecules, certain chemical compounds which have very high energy. When the bonds of these compounds are broken, they release certain amount of high energy which can then be utilized by another molecules for performing different reactions. So in biological systems, we have four energy-rich molecules that are the phosphoenol pyruvate, 1,3-bisphosphoglycerate, ATP, and thioesters. So first of all, we'll discuss about the phosphoenol pyruvate, which is an intermediate in glycolysis. We know that it is the product of dehydration of 2-phosphoglycerate. When a molecule of water is released from 2-phosphoglycerate, it results in the formation of phosphoenol pyruvate. This transfer of phosphoryl group from phosphoenol pyruvate results in the formation of ATP from ADP. Now, this is a substrate level phosphorylation which has overall very high negative standard free energy. Now, this free energy can be utilized by different low energy compounds that require this energy. Now, it can be used by various various reactions, various undergonic reactions. Okay, so this reaction, when the phosphoenol pyruvate is broken and the phosphoryl group is transferred to ADP for formation of ATP, it releases a negative free energy of minus 61.9 kilojoule per mole. Now, out of this total amount of energy which is released, 30.5 kilojoule per mole is conserved as ATP, that is 30.5 kilojoule per mole energy is used for formation of ATP, and the rest of the 31.4 kilojoule per mole energy which is remaining, it can be used for formation of phosphor and hydride bond. So this is a very high energy rich molecule, and the breaking of bond, the breaking of phosphoryl group from phosphoenol pyruvate results in very high negative standard free energy change. Now another energy rich molecule is 1,3-bisphosphoglycerate, which is also a intermediate form during the process of glycolysis. Here the oxidation of glyceraldehyde 3-phosphate results in the formation of 1,3-bisphosphoglycerate, and then 1,3-bisphosphoglycerate eventually leads to the formation of ATP during the process of glycolysis. There is a presence of aldehyde group in glyceraldehyde 3-phosphate, which is then oxidized to carboxylic acid and hydride with phosphoric acid with a standard free energy of hydrolysis, where the standard free energy is 49.3 kilojoule minus 49.3 kilojoule per mole. Here you can see it also has a very high negative standard free energy, and much of this free energy which is released by the oxidation of aldehyde group of glyceraldehyde 3-phosphate is conserved by the formation of acyl phosphate group at carbon 1 of 1,3-bisphosphoglycerate. Now what happens here? You see that glyceraldehyde 3-phosphate has only one phosphate molecule at 33rd carbon. Okay. Now when another phosphate group is added at the first carbon in glyceraldehyde 3-phosphate, it results in the formation of 1,3-bisphosphoglycerate. Now the addition of this phosphate group at the carbon 1, it stores a really high amount of energy. The next step in glycolysis is where the enzyme phosphoglycerate kinase, it catalyzes the transfer of high energy phosphoryl group from carboxyl group of 1,3-bisphosphoglycerate to ADP, resulting in the formation of ATP and 3-phosphoglycerate. Now in the last step we saw that in glyceraldehyde 3-phosphate, another molecule of phosphate is attached to carbon 1, resulting in the formation of 1,3-bisphosphoglycerate. Now again this phosphoryl group present at the carbon 1 of 1,3-bisphosphoglycerate is broken down, and this phosphoryl group is transferred to ADP. And now this ADP is converted into ATP, and again it only has this 1,3-bisphosphoglycerate is now converted into 3-phosphoglycerate. The breaking of bond of phosphoryl group, which is present at the carbon 1 of 1,3-bisphosphoglycerate, it results high amount of negative energy. So here there are two reactions are taking place. So there is a coupling of reaction. Okay, here you can see there is an energy coupling process in which 1,3-bisphosphoglycerate is a common intermediate. It is formed in the first reaction, which is endergonic in isolation, that is, it requires certain amount of high energy for this reaction to take place. We require the system, it requires certain amount of input of energy for formation of 1,3-bisphosphoglycerate. So this is the first step. And the second step is where the acyl phosphate group, which is present at carbon 1 of 1,3-bisphosphoglycerate, is transferred to ADP in the second reaction, and this is a strongly exergonic reaction. So when we will combine these two reactions, the net free energy change is minus 12.2 kilojoule per mole. So here we can see that there is a coupling of reaction where 1,3-bisphosphoglycerate is a common intermediate. The first step is endergonic, the second step is exergonic, and when we'll combine the free energy required in the first step and the free energy released in the second step, when we'll combine the two energies, we will find out that the total standard free energy change is still negative. So when we are combining these two reactions, when we are coupling these two reactions, the net free energy change is negative, and therefore the overall reaction is exergonic in nature. So this coupling process will result in formation of an exergonic reaction. It will lead to the formation of reaction spontaneously. So the outcome of these coupled reactions, both reversible under cellular conditions, is that the energy released and oxidation of an aldehyde to a carboxylate group, and it is then conserved in the formation by the formation of ATP. Here you can see in this diagram also we have the molecule of 1,3-bisphosphoglycerate is combined with ADP. The reaction is catalyzed in the presence of magnesium ion by the enzyme phosphoglycerate kinase, which converts it into 3-phosphoglycerate and ATP. So here you can see in this image that the phosphate group present at C1 of 1,3-bisphosphoglycerate is transferred to the ADP, where it is stored as ATP. Now, the energy currency of cell, that is ATP. It is a very high energy rich compound. It contains significantly large amount of energy in its phosphate bonds. So when the ATP is hydrolyzed to ADP, it results in free energy of minus 7.3 calorie per mole. The three phosphate groups are linked to each other by two high energy bonds called phospho and hydride bond, and whenever one of these phospho and hydride bond is broken, it leads to releasing of high amount of energy, and this is why ATP is known as the energy currency of cell. Now, when first phosphate group is removed by breaking a phospho and hydride bond, it results in the conversion of ATP to ADP. And similarly, when the phospho and hydride bond in ADP is broken, it results in the formation of AMP. But this free energy, it can then be transferred to different molecules wherever they require certain amount of energy. Now, when you will study about any biological pathway, when you study about any biochemical pathway, you will see that there are certain steps in those biochemical pathways where it is coupled with the formation, breaking of ATP into ADP. You will find out that many steps in every biochemical pathway is coordinated with the conversion of ATP to ADP. So why does this conversion of ATP to ADP is taking place? Because the high energy bond, the high energy which is stored in the phosphoanhydride bond of ATP, whenever it is broken, it releases energy, and that energy is transferred to those endergonic reactions. This energy is transferred to those endergonic reaction, and then those endergonic reaction can take place. So this is this free energy which is transferred, which is released from the breaking of phosphoanhydride bond of ATP or of ADP, is then utilized to conclude the reactions. We conclude the biochemical reactions which are essential for biological life. Now, the fourth important high energy rich molecule are the thioesters. The name itself suggests that thioesters are the esters of sulfur, in which the linking oxygen in the ester, the linking oxygen atom is replaced by sulfur, and these thioesters are the common intermediates in various biochemical pathways. You have probably read about the formation of the acetyl coenzyme A, which is the link between glycolysis and Krebs cycle. Similarly, we have malonyl coenzyme A, which is formed during fatty acid oxidation. We have acetyl coenzyme A, propionyl coenzyme A, and so on. So what is this coenzyme A? These are the thioesters, and these are intermediate in several key processes in which ATP is either used or it is regenerated. They participate in the synthesis of a number of other cellular components also, like formation of peptide bonds, in fatty acid oxidation, fatty acid synthesis, in the formation of sterols, cholesterol, vitamin D, terpenes, isoprenoids, porphyrines. So these thioesters, they act as intermediaries of energy during these important biochemical pathways. The most common thioesters are based on phosphopentethymine, which is the biochemically active form of pantothymine. Now, the hydrolysis of acetyl coenzyme A has very high negative standard free energy change. It is associated with minus 7.5 kilocalorie per mole, which is equivalent to minus 31.5 kilojoule per mole. And it is more exergonic than hydrolysis of terminal phosphate of ATP. You can see here that if you remember from the previous slides, that when ATP is converted into ADP, minus 7.3 kilocalorie per mole of amount of energy is released. But here, when the acetyl coenzyme A is broken, the total amount of standard free energy change is minus 7.5 kilocalorie per mole. So definitely it is this coenzyme A, the thioesters, they have much higher energy than ATP. So these are the most important four high energy rich molecules that are present in throughout the life system, throughout all the biological life present uh, on Earth, and they are important for continuity of life because they provide essential energy which are required to continue to carry out the important biochemical reactions that are required for survival of an organism, survival of continuity of life on this Earth. Hope you enjoyed this video. Have a good day and happy study.